Okay, so now that we've completely defined our system, what we want to do is take the Schrodinger equation. It's a differential equation. It's going to be similar to what we did with the classical wave equation. We need to find functions that satisfy this equation. And so if we're looking at just the inside of the box, because outside of the box, the particle can't go out there, so we can ignore the outside of the box. Inside of the box, since the potential energy is zero, this is the Schrodinger equation that we need to solve, where we have negative h bar squared, second derivative of the wave function is equal to energy times the wave function. This is our eigenvalue equation, and we're trying to find the eigenfunctions. And we've also defined our boundary conditions that the wave function has to be zero at the edges of the box, at x equals 0 and at x equals a. So this looks very similar to the problem we just solved in the last chapter when we're looking at the classical wave equation. So we can rewrite this similar to what we did there and put everything equal to 0. So everything is not 0 on one side of the equation. So we'll end up with a second derivative of the wave function with respect to x. All right. And then we can lump all of our constants together. So we'll end up with a 2me over h bar squared times the wave function is equal to 0. And we see this looks very similar, right, to what we saw in the last chapter. So I want you to pause the video, take a look, and see if you can figure out what the solutions to this should look like based on what we saw in chapter 2 looking at the classical wave equation. Okay, so hopefully you took the chance. I understand if you didn't. Hopefully you took the chance to look at this. But what we're going to see is the solutions look exactly the same. This is the exact same differential equation we had before. So our solutions for psi of x are going to look exactly the same. It will be some constant times cosine of some constant times x plus some constant b times sine kx. And specifically, k is going to be equal to 2me square root over h bar. Or we can rewrite this if we want to write out the 2 pi that's part of the h bar explicitly. We can say 2 pi times 2m times the energy raised to the 1/2 over h. All right, so these are equivalent to each other. Okay, so this is our general solution, and now we need to apply our boundary conditions. So our first boundary condition is that psi at x equals 0 is equal to 0. And just as we saw last time, right, that's going to make, because cosine of 0 is equal to 1, that means there's no cosine possible. So that means our first constant, a, is equal to 0. Right, if we come back up here to our equation that I've hidden under my face here, but if we come back up here, this whole term here has to be equal to 0 because if there's a cosine there, it can't be equal to 0. Okay, and then our second boundary condition is just as important. It says that psi at a on the right-hand side of the box also has to be equal to 0. So that means, similar to what we saw before, that k times a has to be some integer multiple of pi. And this is the same argument we had before with our classical wave equation, right? Sine only goes to 0 at integer multiples of pi. And so, what's inside of our sine, the Ka, has to go to 0 when, whenever when x is equal to a, right? So k times a is equal to n pi. All right, and here again, n is going to be integers, 1, 2, 3, ...